this video, we're going to take a closer look at Coulomb's law. Remember that Coulomb's law says the magnitude of the electric force between two charges, Q1 and Q2, equals a constant number, we'll call it K, times the absolute value of the charge Q1 times the charge of Q2, all divided by the distance between Q1 and Q2, we'll call it R, squared. The constant number K equals 9 times 10 to the 9th Newton meter squared per Coulomb squared. Our first exercise involves calculating the force between 2 point charges. The exercise states that we have 2 point charges. Q1 equals positive 5.2 times 10 to the negative 9th coulombs, and Q2 equals negative 4.6 times 10 to the negative 9th coulombs. They are separated by a distance of 7 centimeters. Find the magnitude and direction of the force of Q1 on Q2 and the magnitude and direction of the force Q2 on Q1. This is a two-part problem, so let's start with part 1, finding the force of Q1 on Q2. We need to figure out force direction, which way the force points, and magnitude, how strong it is. Since the two charges have opposite signs, the force between them will attract. It will pull the charges closer together. We can draw an arrow on the diagram to show which way the force of Q1 on Q2 will point. To the left, in the negative x direction. To solve for force magnitude, we'll use Coulomb's law. The problem states that Q1 is positive 5.2 times 10 to the negative 9th coulombs, Q2 is negative 4.6 times 10 to the negative 9th coulombs, and R is 7 centimeters, or 0.07 meters. Let's put all these values into Coulomb's law and see what we find. We'll insert our charges, then our constant K, and divide by the distance between the charges squared. 5.2 times 10 to the negative 9th coulombs times negative 4.6 times 10 to the negative 9th coulombs times our constant K, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared, all divided by the radius, which is 0.07 meters squared. We find that the magnitude of the force of Q1 on Q2 is 4.4 times 10 to the negative 5th newtons. Since we're solving for force magnitude, even though one of the charges is negative, our answer is a positive number. So that's the electric force of Q1 on Q2. How about Q2 on Q1? We can figure it out without using Coulomb's law. Newton's third law says that for every action, there is an equal and opposite reaction. So when Q1 pulls on Q2 in the negative x direction, Q2 pulls on Q1 in the positive x direction with the same strength. On the diagram, the force vectors should look like this. So the force of Q2 on Q1 is 4.4 times 10 to the negative 5th newtons in the positive x direction. Now let's do an example using Coulomb's law to solve for distance between two electric charges. Here's our situation. Two identical charges, Q equals positive 2 times 10 to the negative 10th coulombs, experience an electric force between them of 6 times 10 to the negative 4th newtons. How far apart are the charges from one another? Solving this challenge involves rearranging the Coulomb's law equation. We want to solve for R, the distance between charges, that corresponds to a force between the charges of 6 times 10 to the negative 4th newtons. We start with Coulomb's law as we usually see it. We want to algebraically arrange this equation so it reads R equals something. Our first step is to multiply both sides of the equation by R squared. We'll then divide both sides by F electric. Our last step is to take the square root of both the left and the right side. This gives us the form of Coulomb's law we wanted, the one that lets us solve for R. When we insert the values of Q1 and Q2, which are identical, and the electric force strength, we find that R, the distance between the identical charges, equals the square root of 9 times 10 to the 9th Newton meter squared per Coulomb squared times 2 times 10 to the negative 10th Coulomb squared divided by 6 times 10 to the negative 4th newtons, which equals 7.7 times 10 to the negative 4th meters, or 0.77 millimeters. Solving problems using Coulomb's law often involves two things: figuring out electric force direction and magnitude. You can rely on your knowledge of vectors in charge repulsion and attraction to arrive at direction. And force magnitude, or any other variable in Coulomb's law equation, can be solved for using given quantities and rearranging the equation when needed. Here's another Coulomb's law problem to try. Two electric point charges, Q1 and Q2, are separated by 2 centimeters. The electric force magnitude between them is 3.8 times 10 to the negative 6 newtons. Q1 is an electron. What is the magnitude of the charge Q2? Go ahead and press pause, give it a try, and when you think you have the answer, come back and check your work. Did you get 1.1 coulombs? If so, that's great. If not, let's take a look at it together. The first thing we want to do is write down Coulomb's law and all the parts we were given. We know that K, the Coulomb's law constant, is 9 times 10 to the 9th Newton meters squared per Coulomb squared. We also know from the problem that the electric force between the charges is 3.8 times 10 to the negative 6 newtons. And we're told that one of the charges, Q1, is an electron, which means it has a charge of negative 1.6 times 10 to the negative 19th coulombs. We needed to solve for the magnitude of the second charge, Q2. That means our answer will be a positive number. We know we'll need to use Coulomb's law and that we need to rearrange the equation so that we can solve for Q2. If we rearrange the equation to solve for Q2 by first multiplying both sides of the equation by the distance squared, then dividing both sides of the equation by Coulomb's law constant and Q1, we will have Q2 isolated on one side of the equation. Now we can plug in our values for force, distance, the constant K, and the charge Q1. We find that Q2 equals 3.8 times 10 to the negative 6 newtons times 0.02 meters squared divided by 9 times 10 to the 9th Newton meters squared per Coulomb squared times the absolute value of negative 1.6 times 10 to the negative 19th coulombs, which equals 1.1 coulombs. That's a closer look at Coulomb's law. For more physics in motion, go to our homepage, where the entire series is available to